Yeah, first of all, a big thanks to the organizers for having me and allowing me to give this talk. I actually realized there are many of you here who also visited MuniHac about 2 months ago, where I also gave a very similar talk, actually the same talk. So, but at that talk, we didn't have a chance to actually give a demo. So we're going to do that here. So we're going to do some actual live coding, and hopefully that will be fun. But the first part of the talk will be about LumiGuide, a company that my brother founded about 2 years ago. And yeah, we use Haskell a lot. And I'm going to talk about our product and how we use Haskell. And then the second part will be about OpenCV. It's a library that we are working on also at MuniHac and now at MuniHac. And it's a library that we use pretty heavily at LumiGuide. So a bit about me. I had the fortune to have had a career using Haskell for quite some time now. Now I am at LumiGuide and doing technical stuff. But in a young company, a small company, you have to wear many hats. So I'm also doing about 50% of my time. I'm doing also business development and sales. So. Yeah, I'm not wearing many hats, but sometimes I wear a suit. So the product that we are solving is this. This is a typical site you see in the Netherlands, especially around train stations. Yeah, you need to get on a train and you come here with your bicycle and then like, where should I park my bicycle, right? And that's the problem that we are solving. We help you find a place to park your bicycle. And I have a little video that describes our system, but I don't think we have sound here, so maybe I can just put my mic here at the laptop and then see if that works.
Traffic in Utrecht is steadily getting busier. Some 100,000 cyclists ride through the city centre every day, and their number is growing. All these cyclists look for a place to park their bicycle again and again. Utrecht is looking for smart ways to make bicycle parking at the right place easy for cyclists. One of these smart ways is the new P-Route bicycle. Utrecht is the first city in the world where digital signs are used to guide not only motorists, but also cyclists to free parking places.
Die onderdeel zijn van het systeem, een meetsysteem aangebracht. Achter mij zie je een sensor hangen, die hangen om de paar meter. Dat systeem meet van elke fietsplek of er een fiets staat. En op die manier weten wij meteen hoeveel plaatsen er beschikbaar zijn. En dat wordt doorgegeven naar de borden langs de fietspaden.
Nou, het lijkt me reuze handig om te weten waar de plekken zijn in de stad om de fiets te parkeren.
Right. Okay, so this was actually a project in Utrecht. After that, we went to other cities in the Netherlands. So it's going pretty well. So let's dive a bit deeper into the system and see how it works. So in the video, you already saw that we use these sensors. We actually call them optical sensors. But basically, they are just 2 surveillance cameras. But we mount them to the ceiling in indoor facilities, and in outdoor facilities we mount them to poles. Yeah, like I said, they're basically 2 cameras, but we are actually not storing the pictures that these cameras take, because we only need to analyze them, and then we can throw away the images. So there's no like invasion of privacy. So why do we use 2 cameras? Well, we actually use stereo vision to see in the 3rd dimension. So we don't just look at 2 dimensions, but we can see depth. Here I have a picture of what one of these sensors is seeing. This is actually in an outdoor facility we have in Utrecht City. What you see here is a two-tier bicycle rack, so 2 rows of bicycles on top of each other. What we do is we draw in these regions of interest. That's how we call them. And then for every region, we can see in the third dimension. So, for example, here, where you have no bicycle, our software can't see anything in that space. So we classify that space as being free. But here, when there's an object, doesn't necessarily have to be a bicycle. It can be anything. But our software kind of sees like a cloud of points in that volume, and then we classify it as being occupied. Yeah, like I said, we don't store the pictures of these cameras, so when we released the system in June last year, Sebastian Visser, who actually works at Silk in Amsterdam, he actually parks his bike there at this place actually, and his bike was stolen. And he asked me, okay, can you see who did it? But unfortunately, we can't. Here's another picture of an indoor facility. The nice thing is we don't actually need a bicycle rack to be able to like mount a sensor, which is what our competitors use. They use like physical switches inside a bicycle rack, but we don't need a rack because we can just draw in these regions of interest, and then it will just work. Then what do we do with the information, with the classification of whether a place is occupied or not? Well, we actually send it to displays in the city. In Utrecht we have, I think, currently 26 poles and in total of 52 displays. And yeah, we also have like entrance displays that display how many places there are in that facility, and also even inside facilities we guide people to available space. These things are actually not running Haskell yet, but they will be in some time. But we develop these things ourselves. And then we have management software for the city officials, which they can use to actually get insights into their facilities. This is actually Haskell based, so this is a Haskell web server doing serving the requests, and also providing like what we call live maps, so that operators of a facility can get like an insight into their facility and see how it's being used. And of course we provide lots of nice statistics. Actually, 2 months ago we opened our a facility in Amsterdam, and this is actually our first facility that is fully based on a Haskell image analysis server. In previous facilities we actually used Python to do the image analysis part. The reason we chose Python was that Python has an excellent binding to the OpenCV computer vision library. It's actually maintained by the upstream developers of OpenCV. But at some point, you know, an application grows and grows, and at some point it becomes very hard to manage like a big Python application because it uses a dynamic type system, and yeah, at some point it's very hard to refactor. So we chose to rewrite it in Haskell, and it also, when we did that, it also became much faster, a much more efficient server. So let's dive a bit deeper into the architecture of our system. Well, we have these cameras that you see here on the ceiling. They are connected to a high-speed 1 gigabit Ethernet network. And then they go to a local facility server. So that's actually a server sitting inside the facility, doing the image analysis part. That server uploads its measurements to a central server located somewhere in the data center. Actually, it's running on Hetzer, so it's probably in Frankfurt, somewhere here in Germany. And that server then stores the data. And in fact, of course, we have many facilities, so it looks more like this. Nice thing to mention actually is that all of these systems are running NixOS. So that's another like functional programming part of our system. I'm really excited about NixOS, but that's another talk. So I think that's about all about LumiGuide. So I want to now switch to OpenCV. That's a library that, yeah, because we had to write our server in Haskell, we had to also create our own binding to OpenCV, because there are bindings to OpenCV in Haskell, but they target like an older version of OpenCV, and we actually needed the latest version, the 3.1. It has been open source. You can check it out here. We have quite a number of contributors already. A lot of them are sitting here at this table. Here you actually see a screenshot of one of the experiments we did at our office. You can see that we have a really neatly cleaned up office. This is a little experiment we did where we calculated the distance from the camera to each of these rectangles you see here. And the lighter the rectangle, the closer it is to the camera. And you can neatly see like the shape of the bicycle in here. What I really like about this example is that you can actually see the distance of the floor like increasing from the camera. And that was really amazing to me, that even our algorithm can see like the different, it can even detect the textures in the floor and then calculate the distance through the camera. So that's really nice. So let's dive a bit deeper into this library. One of the core things you need in a computer vision library is a data structure for pictures or for images. And OpenCV actually uses a matrix type for that. You can also use a matrix for representing other stuff like transformation matrices, stuff like that. So we have to wrap that in Haskell. So in Haskell, it's just a new type wrapper to a pointer to the actual C++ matrix. The interesting thing here are these phantom types. And these phantom types statically encode certain information about the matrix. Like, for example, its shape. So how we represent this is we have a list of natural numbers at the type level. And they can encode not only the number of dimensions, but also the size of each dimension. And then we have a phantom type for the number of channels. For example, if you have an RGB image, you have 3 channels for each of the colors. And then the last parameter is the depth, and that encodes if it's like 8-bit color channel or maybe floating point color channel. Oh, it's not working. You can still hear me? Yeah. Okay. Yeah, I'm loud. All right. So now let's look at a little example function. This is a decode function. You put in a byte string, which encodes, for example, a PNG image or a JPEG image, and then you get out a matrix. But then okay, what do we fill in for these phantom types? Well, we know it's a 2-dimensional image, so we have 2 components for the height and width. But we don't really know statically the size of that matrix, because that's encoded in the byte string. We don't know that statically. So what to do here? Well, what we want to encode is that we know something only dynamically, or if we know something statically. So what we did is we introduced this data type called DS for we know something only dynamically, or we know something statically. If you look back at this example, now we can actually make it work. We know statically that we have 2 dimensions, but we only know dynamically what the size of each dimension is. And the same thing for the number of channels and the depth. We only know that dynamically. So with the introduction of this data type, we can actually encode this information. If you look at a slightly more involved example, this is one of the functions we have bound. Let's forget about you put in a source image with a certain height and width, the output image should have the same height and width too. And you can encode that with these phantom parameters. And the same thing holds for the channels and depth. The second parameter is this transformation matrix. And you can see here that it should be also 2D matrix, but it should be a 2x3 matrix. So you can encode that. What you see here over there, that's a monad that we use for representing exceptions, because certain operations can fail, so we wrap it in the except monad. I'm slowly working towards our live demo. The last thing I want to show is that we also have support for mutable matrices. So you can talk and make immutable matrix and then get back a mutable matrix, which you then can actually mutate in either I/O. So this data type is polymorphic, the monad, can either be I/O or ST. The nice thing about the ST monad is that you can have a pure computation, and then you can run an impure computation inside the pure computation, and you can be assured that nothing kind of leaks outside of that. So we have support for both I/O and ST. And of course, what happens in the background is that when you thaw or freeze, that the source image is cloned, so you get a copy, and you can work then on the copy. But we also have unsafe variants that don't copy. But then, of course, you have to ensure that when you put in mutable matrix, that you're not going to mutate it afterwards. Otherwise, your resulting matrix gets mutated too, and then you lose referential transparency. But we provide these for performance, of course. Now, let's actually now do the demo and see if we can play with it. So this is Will, my brother. What we're going to do is we actually will support. We actually build in support for opening your webcam. And what we're going to do is, first example is actually opening the webcam and then just showing that on the screen. Actually, let me stand right here. So what you see here is we import the OpenCV library. The OpenCV module is all you need. You get all the functionality. There are other modules that you can import if you want to have a more granular import. So what this example will do is it will open, create a new video capture object. Then it will open the webcam. This is the video device source, actually the first kind of camera detected on the system. Then it will create a window, and then we have a loop which will grab a frame, and then it basically when you grab a frame, for performance reasons, you do not immediately get the image. And for instance, skip a few frames, so just grabbing a few, then you retrieve the image, and you actually get a matrix in your program. Or not, because the end of the video. Yeah. So here when we have the image, we actually show it in the window, and we wait for a key. And when the key is 27, which is the escape key, we exit. Otherwise, we just continue. Okay, so let's actually run this program and see if it works. There we go. Okay, that's cool.
You can see at the top, the CPU use is something like 15%. I think it's actually limited by the frame rate of the camera.
Right, yeah. So now we want to actually start playing with this example and perform some image processing steps on these images. So let's actually go to the...
Escape keys were.
It isn't?
Well, maybe it's a focus issue. Yeah, we can just kill it on the...
Oh, yeah.
So it's like...
Oh, it's not responding.
Yeah, it's working, but
Oh, yeah, all the input got lost. Wait a minute. There we go.
Oh,
it just
so
lagged a bit.
It
Okay.
queued all the.
All right. Okay, so let's go to the second example, and then in the second example we will actually blur the image a bit. So we perform a filter on them. All right. So, the first thing we're doing is we are actually introducing this process function, which we call right here. So you get your source image, and we pass that through process, then we get a new result, and we actually show that result. All right. But this function is actually not doing anything.
Well, we do conversion, right?
Sure. So you put in a source image, and here you can see the type. It's we know it should be a 2D image, but we only know the height and width and the channels and the depth. We know it dynamically. But what we want to have is a 2D image with three color channels and 1 byte each. So we have to coerce this input image to this type. And when this this value doesn't have this representation, this function will actually fail. And we turn that into, when that fails, it will be turned into exception. We also have an unsafe coerce. If you kind of statically know it is the case, then no dynamic checking will be done. Do we have an example of this too? It's exactly the same, right? So let's now move on to doing something interesting there. What we're going to do is we're going to blur the input image a bit. So we're going to call Gaussian blur, which can also fail, so we have to wrap it in this pure accept thingy, because this is like a pure computation. And we are in an I/O monad here, so we have to, if this computation throws an exception, we lift it into this monad via this function. So actually, let's run this and see if it works. There we go. So what we actually want to do with this example is we want to run a canny edge detector on it, and then also the detection of straight lines. That is what we are working towards, as you said. But then doing a bit of blurring beforehand is a good way to not have too many edges in your image. So let's actually now go to the fourth example that runs a canny edge detector. So it's still the same program. Here we do the Gaussian blur. And now we're going to run a canny edge detector on the blurred image. And then we should get back edges. Actually, the nice thing to say is this edge image, we haven't provided the type here. But this is actually as a black and white image. So it has only one color channel, an 8-bit color channel.
In preparation for the next example, we also converted back to a color image.
Yeah, because we want to show this edge image, but it's a black and white image, and this function here expects a 3-color image. So we convert it from gray back to blue, green, red, and then we can show it again. So let's run this and see what happens. All right. Cool. Yeah.
Maybe you can introduce a small error.
Sure. Yeah. Go ahead.
Like say, oh, we are converting from gray to blue, green, red. Let's say exactly from red, green, blue to blue, green, red. So it should be like a type error.
And also see.
Oh yeah. Output match type 3 with 1. So that means when you're converting RGB image to something else, it means your source image has to have 3 channels. But because we ran the canny edge detector, it only has 1 channel, so it's a standard type error, which is really nice. just the gray is just distributed over all three channels equally. So to stop them, nothing will happen. Otherwise, the blue and red will be converted.
So this candy edge detector doesn't work on the color?
It can work on a color image, but it produces a single channel grayscale image.
Do you have got the names of the channels in the chart as well?
No.
This
No.
is a difficult part because basically matrix is like this data and no encoding, like a byte string. So you lose all information about what exactly is being represented. So it's a challenge to also encode that in pattern files and preserve information. That's a challenge.
Yeah, maybe we can move to the next example. In the next example, we are going to run another filter step on the image produced by the candy edge detector. And what we are going to do is we are, let's see, where is it? Oh, this is the new part. Okay, no. What we're first going to do is we're going to what we want to have is we want to see the source image, but then with the edges drawn on top of it. So what we're going to do is we're going to create a new matrix here with this with mod function. You pass it the information like the height and width of the image that you want to create, and the number of channels and the depth. And then you you should say, okay, what should be the initial color of the image, and in this case it's white. And then you need to pass it a function that gets a mutable matrix, and then this function is going to write to that image. And what we're going to do is we're going to copy the input image, so the original image, into the output image, and then at the same location we are going to copy the edges on top of it. But of course, if you would do this, maybe we can try this. Well, if you change this to nothing. Of course, what will happen now if you draw them on top of each other, then you will only see the edges, and that's not really what we want. So let's see. This is MuniHac 4. Yeah. Oh, 5. Sorry. Yeah. So this is not what we want. What we actually want is to see the source image behind it. So what you can do with the copy to function is you can give it a mask, and the mask will tell you, okay, copy the image, but only where the value is in this case
Not zero.
Not zero. Yeah. And we actually for the mask we actually use the edge image because that's just a Boolean or a black and white image. So now we should get a nice result. Yeah. There we go. Another cool thing now to do is to run another filter on it to detect straight lines. OpenCV provides a function for that. So here we go. We still have the same example, but we are introducing, where are we?
Yeah,
there we go.
This is all the same.
Yeah, maybe you can explain, Roel.
Yeah, actually we run it here. It's the U lines detector, the probabilistic version. It's just some statistical algorithm which can detect straight lines in a binary image. So we run it on the edges found by the candy edge detector. But actually this algorithm destructively updates the input image. So we can't just run it on the original image because it's not mutable. So we first take the edge image calculated in this line, and then we draw it, and we get a copy which is mutable here. We call it edge image M for mutable, and we plug that into the lines function. And there are some parameters saying something about the resolution, the maximum length, the minimum length of lines, the apps allowed. But it produces just a nice vector of lines, which we then want to draw, otherwise we won't see anything. But that's what happens here. You just iterate over each line segment part. Is there a question? Yes?
So is there a difference
different types. We have a new type wrapper called MUT, or mutable, and it's actually just a matrix wrapped in the mutable new type. And all the functions, it's a type error that makes them. So here we loop over the line segments, and we basically just use another CV drawing function. This also draws on a mutable image, draws all the line segments in the red lines.
Yeah.
Well, let's see what happens. 6.
There we go.
And then you can imagine using the found lines to maybe build a 3D model, because you know perspective and everything.
Yeah. Maybe we can introduce another bug, see if the type checker catches it. For example, if we...
Let's use the non-mutable...
Oh yeah, that was the question. If we put in a non-mutable image, hopefully the type checker will complain. There we go.
Expected type, here you see the mutable thingy.
Yeah, so you can, it's kind of a good error message. It says, okay, can't match expected type MUT, and you see a big pile of that, but with actual MUT. So there you can see, okay, I should have put in a mutable matrix. Similarly, we might be able to maybe change here the number of channels to 4, see if that catches it. Yeah. And now that should give an error, because can't match 3 with 4, because we're putting in a 4 and we are telling GHC that we want to have a 3-channel image, so it nicely catches that.
Because you now have to basically entering the same text and the type of, you can basically refactor that using type variables. It's called type variables, and you don't have to type in 3 all the time. Yeah. Even if you have to type it like here, it has to be correct or you didn't type out.
Yeah, let's move on to the last example. If you look at this this example, you might want to tweak certain parameters to tweak your algorithm. And it's very cumbersome to actually, tweak the parameters in your code and then compile it again and then see the result. You really want to have a more tight feedback loop. So OpenCV in its kind of GUI library, it's called HiGUI. They also have support not only for Windows but also for very simple widgets like track bars. And we also bound those. So you can create a track bar here on this window. You give it a name and the starting value and the end value, and then you should give it a callback function that gets fired when you change the track bar, and the callback gets the position of the track bar, and then what we do is we create an IO ref that stores the information, and then we write to the IO ref when you move the track bar, and then in our loop or in our process function, we actually read those IO refs, and then we use that as the input parameter. And then we pass that to the, what do we change? The canny edge detector, yes. the parameters for the canny edge detector, the low and the high threshold.
The sensitivity of the edge detection.
So let's run that and see if that works. Okay, so you see the track bars on top. And when you change them, you can see the output changing as well.
It's in the same escape key, isn't it?
Oh. Maybe change it, swipe like that worked before. That's weird. It's selected, right? Oh, no. Wait, what if you do?
It's Murphy's law. Oh, it went to. Yeah, you can control it. Yeah, yes. Oh, it's really slow.
What's happening?
Yeah, it's some kind of buffering of the key process, and I promise you, it's working.
Let's do this. Oh, even.
make a quick show.
Okay, this is not working. Oh. Okay, it's a bit weird, but well, what it also is, you can see the edges being adapted to these settings. Yeah, I think how am I doing time-wise? Pretty good. Yeah, so that's oh, there we go. Yeah, now I think it's working. No, it isn't. Damn it.
Yeah, maybe you can show it here. See the audience. Okay, let's make it really sensitive. Yeah, now you can see you can just get garbage. And usually with these vision algorithms, you want to tweak some values. You can't really predict what value you need. So it's really nice. You just have to track bars and just get immediate feedback of what's happening. And, it's really easy to do.
All right. Yeah, that was the demo. So thank you for bearing with us. And that's actually pretty much all of my talk. I have a few more slides, but I don't think we have too much time left to go over them. So if you have questions, then